Hello everyone, I'm Chung-Ming, and today I'll be talking about our work at ASRU, Future Spoken Language Understanding via Joint Speech-Text Models. And this is a joint work of TTIC and University of Chicago folks, including me, Mingjia Mei, Zhujie, and Karen. And first is a highlight of our work. In this work, we use speech-text models for the task of few-shot and zero-shot spoken language understanding. With our method, we are able to match the performance of previous models with as little as 20% or less of speech data. And in addition to the good performance of our method, we also analyzed the pre-trained and fine-tuned speech-text models to understand and explain why the speech-text models have the ability to transfer the knowledge learned from text-based fine-tuning to speech. And for this analysis, it also suggests that by fine-tuning the model with bottom layers frozen, we can actually get better performance in a zero-shot scenario. So first, I'll be giving some background knowledge of the pre-trained speech-text models. And in this work, we use some pre-trained speech-text models in previous papers, including SpeechLM and SpeechUT. And because they share a very similar architecture, so I will be explaining them together. For this kind of model can take either speech and text as input. And for speech input, there is an additional speech transformer encoder to encode speech signals into a sequence of vector representations. And for text input, there is a simple embedding table to encode text into vector sequence. And then for either speech or text representations, there is a shared transformer on top to combine the two different modalities into a shared model. And then there are some different losses used to train the model. For speech and text input, there are self-supervised losses defined on them separately. And also there are some additional loads to encourage the speech representations to be more discretized, so they can be more similar to the text representations. Yeah, so the first part of this work is to study how can we apply the pre-trained speech-text models for zero-shot and few-shot spoken language understanding. So first, in our work, we assume that we only have limited labeled speech data, but more text data, which is a very practical scenario because in the real world, in general, speech data is more difficult to collect than text data. So here are some different fine-tuning scenarios we consider. The first one is a traditional approach. We fine-tune the model with all speech data. And the second and third ones are the proposed few-shot and zero-shot scenario. In the few-shot scenario, we assume we have very little speech data, but more text data. And in a zero-shot scenario, we use only the text data during fine-tuning. But no matter how we fine-tune the model, when we are testing the model, we always use speech as an input. And in this work, we use a slew benchmark to study the spoken language understanding of speech-text models. And there are two major tracks in the slew benchmark. The first one is sentiment analysis, where the model is asked to classify the sentiment of an utterance to be positive or neutral or negative. And then there's another task named entity recognition, which is a sequence labeling task. And we study the speech-text models fine-tuned with different amount of speech data and also more labeled text data. And the fine-tuning details, for example, like number of training steps and the batch size, something like that, all follow the default setup in the slew benchmark. So the first result we show here is the sentiment analysis result. And we can see in the table the speech text model without using any speech data can actually reach a comparable performance than previous models, which uses the full amount of speech training data. So this result suggests that the speech text models have a good zero-shot ability for the sentiment analysis task. And in the second figure here, we show the result of the named entity recognition. And in this figure, there are some points to highlight. The first one is that in one of our speech text models, the speech UT have a very good performance, very good zero-shot performance, which is almost 50% of F1 score. So in this case, we don't even use any speech data to fine-tune the model on language understanding. And then the second thing to note is that when we are comparing the models fine-tuned with speech and text and fine-tuned with speech only, we found that the models fine-tuned with speech and text is in general better than the speech-only fine-tuning. And the last thing is that when we are comparing our speech text models, we find it actually can outperform the previous work, Hubert, which is a speech-only models, with as little as 20% of the speech data. Okay, then we're going to move to the second part of our work, the analysis of pre-trained and fine-tuned speech text models. First, the tool we use to analyze the pre-trained representations is called the average neuron voice correlation. And in this matrix, we assume there are two random variables, x and y, representing different views of the same data instance. And the average neuron voice correlation basically computes the correlation between the two sequences of representations. So to be more specific, here we show an example where we have a text encoder encoding a paired speech and text data. And the speech and text data are encoded into a sequence of vectors. And here you can see the first position in the vectors represent the activation of the first neuron, and the second one is activation of the second neuron, and so on. So, and here we can collect all of the activation values of the first neuron given the speech input to be x1, and then the same activation values given text input as y1. And then we can assume we have a perfect speech text encoder. Then theoretically, x1 and y1 should be very similar to each other. So when we are measuring the correlation between x1 and y1, it's actually measuring whether the speech and text representations are aligned well in the speech text models. And you can also use the ANC in a different way. For example, here, another example is we use a pre-trained and a fine-tuned transformer and use exactly the same input to both models. And in this case, the ANC scores between the two different representation sequences will be evaluating how much the pre-trained and fine-tuned models differ from each other. Okay, so here this figure shows the degree of alignment between speech and text representations, which is the first setup. So in this figure, you can first notice that the degree of alignment increase over the layers, especially in the bottom layers, which shows that the speech text models actually learns to align the speech and text representations in the bottom layers. And on the other hand, you can also notice that the pre-trained and fine-tuned models are very similar to each other in the bottom layers, but they differ much more in the top layers. So this By this observation suggests that the fine-tuning mostly affect the top layers and leave the bottom layers unchanged. And in the following figure, we are using the second scenario of ANC score, where we are comparing how much the pre-trained and fine-tuned models differ from each other. And here we compare two different setups. The first one is we fine-tune the models with the same task, but with different input modalities. And the second scenario is we fine-tune the models on different tasks with the same input modality. So you can see the first group consistently get higher ANC scores than the second group, which shows that actually the task have a larger impact on the ANC score than the input modality, especially to the top layer, for the top layers in the speech-text models. So here we like to have a little conclusion of our analysis. The first one is that in the speech-text models, the bottom layers align speech and text representations in a shared representation space. So here we got an inspiration, like this aligned representation shouldn't be affected too much during a fine-tuning time. Otherwise, the aligned representation may be destroyed. And the second observation is that the top layers are task specific. So this part should be fine-tuned when we want to adapt this pre-trained model to a new task, specifically a language understanding task. So here we got an inspiration. How about we just fine-tune the top layers and keep the bottom layers frozen? And then this figure here shows a result of fine-tuning model with the bottom layers frozen. So the first thing to note here is when we freeze part of the bottom layers in the speech-text model, in the old speech and few-shot scenario, we only see a very little performance reduction. But on the other hand, for the zero-shot scenario, we can see a very significant improvement in terms of the final performance of the models, which shows the model actually can have a better transferability from text to speech when we freeze the bottom layers. Okay, so here comes to our conclusion. First, in this work, we study the use of speech-text models for the task of few-shot spoken language understanding. And we shows that the speech-text models have a very good transferability from text to speech. And also, the few-shot performance in our work matches the previous work trained on the full amount of speech data, but we only need 20% of the data they used. And also, we do some analysis to speech-text models, and the analysis shows that the bottom layers in the speech-text models are task-agnostic, and the top layers are task-specific. And based on this observation, we propose to, when fine-tuning the model, we propose to freeze the bottom layers and only fine-tune the top layers, which result in a better zero-shot performance. Okay, so this is then the end of my presentation. And if you find this topic interesting, you are free to reach out to us and to have any further discussion.